Good evening, my friends. Thomas here, inviting you to join me for another night of gentle questions and timeless journeys. Tonight, I'd like you to picture something extraordinary. Imagine stepping outside on a clear night and looking up to find not one, but two moons hanging in the darkness above you. Two celestial companions, each casting their own silver light across the landscape, their shadows crossing and merging as they drift through the star-scattered sky. What if Earth has had more than one moon? What if, somewhere in the deep corridors of time, our planet kept company with multiple lunar siblings? It's a question that reaches beyond simple curiosity. It touches something fundamental about our place in the cosmos, because some scientists think it's not just possible, but that we may have proof. You see, for as long as humans have gazed upward, the moon has been our constant companion. In prehistoric times, before clocks or calendars, people tracked its changing phases to measure the passage of time. By its silvery light, travelers could navigate at night, and farmers could extend their work after sunset. The moon became what some call a cultural mirror, reflected in countless legends and beliefs across every civilization. The ancient Romans worshipped Luna, the Greeks knew her as Selene, and in Chinese lore, the moon is home to the goddess Chang'e and her companion rabbit. Even our language carries these lunar echoes. The word lunatic derives from lunar, echoing old ideas that the full moon could stir madness in the human heart. But beyond myth and timekeeping, the moon profoundly influences Earth's natural systems. It tugs on our oceans to drive the daily tides. Its stabilizing pull keeps Earth's axial tilt in check, giving us the regular seasons we depend upon. Without it, our planet's tilt would wobble chaotically, potentially swinging between extremes, ice ages sweeping different regions every few thousand years. So, as you settle in tonight, perhaps with the moon's light filtering through your window, I invite you to join me in exploring this fascinating possibility. Has Earth ever harbored a second moon in its ancient past? What evidence might we find hidden in lunar rocks or Earth's geological record? And what would it mean for our tides, our climate, our very evolution, if another moon graced our skies? Take a deep breath. Let the day's urgencies fade. Together, let's journey through scientific findings and theories, through evidence both solid and speculative, to understand what an Earth with two moons might entail. We'll separate confirmed facts from scientific dreams, and along the way, we'll discover that the neat one-moon system we take for granted may have been far more crowded long ago. The night is young, and our questions are timeless. Let's begin. Let's turn our gaze now to the moon. We know this faithful companion that has journeyed with us through all of human history. Picture it there, hanging in tonight's sky. Our moon is a world roughly 474 kilometers wide, about a quarter the diameter of Earth. If you could hold Earth as a nickel in your palm, the moon would be like a coffee bean circling slowly around it, held by invisible threads of gravity at an average distance of 384 kilometers. It's our nearest cosmic neighbor, the fifth largest natural satellite in the solar system, and it endlessly presents the same weathered face to us, those dark Maria plains and bright highlands that our ancestors saw as a rabbit, a man, or a maiden, depending on where they stood on Earth. But how did this moon come to be? And why just one? The story begins in violence, in the very childhood of our solar system, about 4.5 billion years ago, and I want you to try to imagine this span of time. These billions of years, like pages in a book so thick you could never finish reading it when Earth was still young and molten, still glowing with the heat of its formation. Something extraordinary happened. A wandering world, a protoplanet about the size of Mars that we now call Theia, found itself on a collision course with our infant Earth. Picture that moment. Two worlds, each with their own destiny, their own possible futures, hurtling toward each other through the darkness. When they met, it wasn't a gentle encounter. In an impact so tremendous it defies imagination, Theia and Earth tore each other apart. The collision was so violent that both worlds essentially liquefied, their rocky mantles mixing, their cores merging. A vast cloud of molten rock and vapor was ejected into space, debris glowing white-hot, a ring of liquid stone circling what remained of Earth. You might imagine standing on some distant world, watching this cosmic catastrophe unfold. The sky around Earth would have been filled with glowing debris, like a crown of fire. And then, over time, perhaps just a few years, perhaps decades, gravity began its patient work. The debris began to pull together, drawn by its own mass. Droplets of molten rock merged with other droplets. Boulders found boulders. The ring became clumps, and the clumps became a sphere. Our moon was born. The evidence for this violent birth is written in the moon's very bones. When the Apollo astronauts brought back those precious pounds of lunar rock, and think about that for a moment, humans actually walking on another world, carrying pieces of it home in their pockets, scientists made a remarkable discovery. The moon's rocks are strikingly similar to Earth's. The ratios of oxygen isotopes, those atomic fingerprints that every world carries, are essentially identical between moon rocks and Earth rocks. It's as if the moon is Earth's child, or perhaps more accurately, Earth's sibling, born from the same catastrophic moment. The lunar samples revealed something else. The moon had once been completely molten, covered in a deep magma ocean that gradually cooled and crystallized. The lighter elements that should have been there, the volatiles that would have given the moon an atmosphere, water, the ingredients for life had boiled away in the intense heat of its formation. What remained was a dry, airless world of rock and dust, forever marked by its fiery birth. But here's where the story becomes even more wondrous. That early moon, that newborn satellite, wasn't where we see it today. Scientists estimate the moon may have formed only about 19.0 kilometers from Earth's surface, just 1.5 times Earth's own diameter away. Can you imagine looking up at such a moon? It would have dominated the sky, appearing perhaps 15 or 20 times larger than it does now. A full moon wouldn't have been a distant disk, but a vast, looming presence, so bright that night would hardly have existed. You could have seen individual craters, mountain ranges, perhaps even watched as meteors struck its surface in real time. And this young moon moved fast. Instead of taking nearly a month to orbit Earth as it does now, it completed its circuit in just a few days. Earth itself was spinning rapidly. Then a day might have lasted only 5 or 6 hours. Imagine that. The sun racing across the sky, barely time for the land to warm before darkness fell again, and then that enormous moon rising, flooding the world with silver light before dawn came racing back. You might wonder how we got from that frenetic early dance to the stately waltz we see today. The answer lies in the tides. The moon's gravity raises bulges in Earth's oceans. We see this as our daily tides. But Earth's rotation carries these tidal bulges slightly ahead of the moon, and this gives the moon a gentle forward pull, like a child being spun faster on a merry-go-round. This transfers energy from Earth's rotation to the moon's orbit. The result? Earth's days grow longer, and the moon spirals slowly outward. This has been happening for 4.5 billion years. The moon recedes from us at about 3.8 centimeters per year, roughly the rate your fingernails grow. It's almost too slow to comprehend, yet over geological time, the effect is profound. Fossil evidence tells us that 400 million years ago, in the Devonian period when the first forests were spreading across the land, Earth's day was only about 21 hours long. There were 400 days in a year back then, each one brief and hurried compared to our leisurely 24-hour cycle. Today, after all those billions of years of this cosmic dance, the moon has reached a distance where it takes about 27.3 days to orbit Earth. It's settled into a rhythm we call tidal, locking the moon rotates exactly once for each orbit, which is why we always see the same face. Those dark Maria, those bright highlands, that pattern that might be a face or a rabbit, it never changes, never turns away. The far side of the moon remained a complete mystery until we sent spacecraft to photograph it. And what we found there would later provide a tantalizing clue that Earth might once have had more than one moon. But we'll return to that mystery. Let me tell you about what this moon means for Earth, beyond the poetry and the moonlight. Its presence profoundly affects our planet's systems in ways both obvious and subtle. The tides it raises don't just move water, they've helped shape the evolution of life itself. Think about those ancient tidal pools, billions of years ago when the moon was closer and the tides were enormous. Walls of water, perhaps hundreds of meters high, would have swept across the landscape. These massive tides would have stranded sea creatures in pools that dried and refilled, creating evolutionary pressure that might have helped drive life's first tentative steps onto land. Even now, countless species time their lives to the moon's rhythm. Corals spawn by the full moon's light. Sea turtles emerge to nest when the moon is dark. Grunion fish ride the highest tides onto California beaches to lay their eggs in the sand. The moon is woven into the very fabric of life on Earth. But perhaps the moon's most crucial gift is stability. Earth's axis is tilted at about 23.4 degrees, and it's this tilt that gives us our seasons: summer when we lean toward the sun, winter when we lean away. Without the moon's steadying gravitational influence, Earth's tilt would wobble chaotically. Computer models show that Earth's axis might swing between 0 and 85 degrees over millions of years. Sometimes Earth might spin nearly upright with no seasons at all. Other times it might tip nearly on its side, with the poles alternately baking under constant sun and freezing in endless night. Mars, with its 2 tiny moons that provide no meaningful stabilization, experiences exactly this kind of chaos. Its axial tilt has varied between 15 and 35 degrees over the past few million years, triggering massive climate changes that may have destroyed any chance for sustained habitability. But Earth, anchored by its massive moon, maintains a steady tilt. Our seasons remain predictable, our climate stable enough for complex life to evolve and flourish. And that brings us back to our question, what if Earth had possessed more than one moon? How different might our world have been? I want you to imagine standing on a beach, perhaps millions of years ago, when the moon was closer. The tide is going out, and in the wet sand you can see the tracks of early creatures, perhaps some of the first to venture from sea to shore. The moon hangs huge in the sky, and Earth's rotation is slowing, imperceptibly, but inexorably, with each passing tide. This is the world the moon has made, a world of rhythms and cycles, of stability and change, all orchestrated by that silver sphere above. But the moon also holds mysteries. Its 2 faces, the familiar near side with its dark maria and bright highlands, and the far side, thicker crusted and more heavily cratered, tell different stories. Why should the moon be so lopsided? Why does the far side look so different from the face we know? Some scientists have proposed a remarkable answer. Perhaps Earth once had a second, smaller moon that eventually collided with our larger moon, spreading its material across the far side like cosmic plaster. It's a tantalizing thought that makes us wonder, could Earth have harbored other moons in its past? The moon's own orbit offers another puzzle. It's tilted about 5 degrees to Earth's orbital plane around the Sun. Models suggest that right after its formation, the moon's orbit should have been inclined more steeply, perhaps 10 degrees or more. Something damped and altered that tilt over time. Could it have been gravitational interactions with other moonlets, debris, or a disk of material that has long since dissipated? The very angle of the moon's orbit might be telling us that Earth's gravitational neighborhood was once more crowded than it is today. Consider, too, the moon's profound influence on our perception of time itself. Long before humans invented clocks or calendars, the moon's phases provided a natural timekeeper. That cycle from new to full and back again, roughly 29.5 days, became the basis for the month in calendars worldwide. The very word month comes from moon. Our ancestors planned their planting by the moon, traveled by its light, held festivals at the full moon. Even now, though we have atomic clocks that can measure time to extraordinary precision, many cultures still celebrate lunar calendars, still mark holy days by the moon's phases. The moon has been our companion through all of human history and far, far longer. It was there when the first life stirred in Earth's oceans. It watched as continents drifted and mountains rose. It witnessed the rise and fall of the dinosaurs, the spread of flowers across the land, the first humans looking up and wondering what that bright disk might be. You know, sometimes I step outside on a clear night and look up at the moon, and I try to really see it not just as a bright disk in the sky, but as a world, a place with mountains taller than Everest, with valleys deeper than the Grand Canyon, with a history written in billions of craters. I think about those 3.8 centimeters. It moves away from us each year, and I realize that the moon our distant descendants see will be smaller in the sky, more distant. In about 600 million years, the moon will have receded so far that total solar eclipses will no longer be possible. That perfect coincidence where the moon exactly covers the sun's disk, something that may be unique in all the cosmos, will be lost forever. But for now, for this cosmic moment we inhabit, we have this perfect moon, not too close to make Earth's rotation chaotic, not too far to lose its stabilizing influence, not too large to create destructive tides, not too small to be ineffective. It's almost as if the universe has given Earth exactly the moon it needed for life to flourish. And yet, science tells us that Earth has captured other, smaller moons from time to time. Right now, as you listen to these words, there might be tiny asteroids, no bigger than cars, temporarily caught in Earth's gravity, making a few loops around our planet before wandering off again. We call them mini-moons, and they remind us that the Earth-Moon system isn't closed and static but dynamic, still capable of surprise. What if one of these captured objects had been larger? What if it had stayed? What if Earth's gravitational arms had held onto a second permanent moon? The questions beckon us forward, toward an exploration of how moons form and die, of evidence for lost lunar companions, and of what our world might have been like under the light of two moons. The moon we know has been Earth's patient sculptor, carving our days longer, pulling our tides, steadying our seasons. It has been witness, companion, and guardian. But was it always alone in these duties? That's a question that will carry us deeper into the night, deeper into wonder. Perhaps you can feel the moon's gravity even now, not just physically in the tides, but in something deeper, that ancient pull that makes humans look up and dream of other worlds. That same pull that once made our ancestors track its phases and tell stories about its face. The moon connects us to them, and to all life on Earth, in an unbroken chain of light and shadow, of months and tides, stretching back 4.5 billion years to that moment of violent birth when worlds collided and our moon was born. Perhaps you can feel the moon's gravity even now, not just physically in the tides, but in something deeper, that ancient pull that makes humans look up and dream of other worlds. And to understand how Earth might have gained or lost moons throughout its long history, we need to understand something fundamental: how moons are born. Let me invite you to imagine the early solar system, 4.5 billion years ago. Picture a vast disk of dust and gas swirling around our young sun, like cream stirring slowly into coffee. Within this disk, particles are colliding, sticking together, growing from specks to pebbles to boulders to worlds. This is where the story of every moon begins, in violence or in gentle accumulation, in capture or in creation. There are only a few ways that nature knows how to make a moon, and each one leaves its fingerprints in the orbits and compositions we see today. The most dramatic way to forge a moon is through cosmic collision. This is how our own moon was born, as we've discovered through decades of patient detective work. When the Apollo astronauts brought back those precious pounds of lunar rock, scientists found something remarkable. The moon's composition is eerily similar to Earth's. The oxygen isotopes, those atomic signatures that are like fingerprints for worlds, are essentially identical between moon rocks and Earth rocks. It's as if the moon is made from Earth itself, which in a sense, it is. Imagine, if you can, the moment of impact. A world the size of Mars, which we've named Theia after the mother of the moon goddess Selene, approaches Earth on a collision course. Not a direct hit, but a glancing blow. The speed is unimaginable, perhaps 10 kilometers per second, fast enough to circle our entire planet in just over an hour. When Theia strikes, the energy released is beyond comprehension. Both worlds are torn apart at the point of impact. Rock doesn't just melt, it vaporizes, turning into a cloud of superheated gas that glows brighter than the sun. What happens next is like watching the birth of a phoenix from its own ashes. This cloud of vaporized rock, made from both Earth's mantle and Theia's remains, spreads out around our wounded planet in a disk. Earth itself is molten, glowing orange and red, its day shortened to just 5 hours from the tremendous angular momentum of the impact. And in the disk above, something remarkable begins to happen. The particles start to cool, condensing like rain from a cloud, but instead of falling back to Earth, they begin to find each other in the darkness. You might wonder how long this takes. Not millions of years, as you might expect, but perhaps just a few decades or centuries. Computer simulations show us this ancient disk glowing and churning, with particles colliding and sticking together through their mutual gravity. Some fall back to Earth, adding to our planet's mass. Others are flung out into deep space, lost forever. But in between, in that sweet spot where gravity balances perfectly, chunks begin to grow. First to the size of mountains, then small asteroids, then something larger. In some simulations, multiple moonlets form, initially 2, 3, even dozens of small moons orbiting the infant Earth. Imagine that sky, instead of one moon, a collection of smaller worlds racing around the planet, their surfaces still glowing with the heat of their birth. These moonlets wouldn't last long on cosmic timescales. They would interact gravitationally, pulling on each other, disturbing each other's orbits. Some would collide and merge. Others might be ejected from Earth's orbit entirely. Eventually, one would grow dominant, sweeping up its siblings until only our moon remained. This is the power of a giant impact. It can create not just one moon, but potentially several, though only the strongest or luckiest survive. We see this elsewhere in our solar system. Pluto's large moon Charon was likely born from a similar collision, though in that case, Charon is so large relative to Pluto, more than half its size, that some astronomers call them a double dwarf planet system. Had Earth's impact been slightly different, perhaps we too would have ended up with 2 moons of more equal size, forever circling each other as they circled us. But not all moons need such violence to be born. Let me take you now to a gentler form of creation, one that happens not in hours or years, but over millions of years of patient accumulation. This is co-formation, when moons grow up alongside their parent planet like siblings raised together. To understand this, we need to journey outward in our solar system, past Mars and the asteroid belt, to where Jupiter was born. As the giant planet gathered its enormous mass from the disk around the Sun, it created its own miniature disk, a swirling cloud of gas, ice, and dust that orbited the growing world. The temperature in this disk varied with distance from Jupiter. Close in, where it was warmer, rocky materials could condense. Farther out, where it was colder, ice could form as well. Picture yourself floating above this ancient disk around Jupiter. Below you, the giant planet is still glowing with the heat of its formation, a dim orange orb shrouded in thick clouds. Around it, the disk spreads out like a vinyl record, but one made of countless particles all orbiting in the same direction, in the same plane. Within this disk, the same process that built the planets is happening in miniature. Particles collide and stick, pebbles become boulders, boulders become mountains. And in special places in the disk where the temperature and density are just right, these growing bodies sweep up material faster than their neighbors. This is how the four great Galilean moons of Jupiter were born: Io, Europa, Ganymede, and Callisto. They formed in sequence, each in its own zone of the disk, each with a composition that reflects the temperature at its birthplace. Io, closest to Jupiter, is dense and rocky, made of materials that could withstand the heat. Europa, a bit farther out, has a rocky core but also water ice. Ganymede and Callisto, in the colder reaches, are half ice by mass. It's like a family portrait where you can see the conditions of their childhood written in their very substance. What's remarkable about co-formation is how orderly it is. These moons orbit in nearly perfect circles, all in the same plane, all moving in the same direction as Jupiter's rotation. They're like a perfectly choreographed dance that's been going on for 4.5 billion years. If Earth had formed moons this way, perhaps if our planet had been more massive and had its own substantial disk, we would have a very different sky. Instead of one large moon in a tilted orbit, we might have several smaller moons, all orbiting above our equator, their regular motions as predictable as clockwork. The third way to gain a moon requires no creation at all, only opportunity and timing. This is capture when a planet's gravity snares a passing asteroid or comet, pulling it from its path around the sun into a new life as a moon. It's perhaps the most chaotic and unpredictable way to acquire a satellite, and it can happen at any time in a planet's history. Let me paint you a picture of how this might occur. An asteroid, perhaps one that's been wandering the solar system for billions of years, approaches a planet on what seems like just another flyby. It's happened before. The asteroid has passed near planets many times, each encounter slightly altering its orbit around the sun. But this time is different. This time, the geometry is perfect. The asteroid approaches at just the right angle, at just the right speed. As it falls toward the planet, accelerating in the gravitational field, something else happens. Perhaps it passes close to an existing moon, or skims through the planet's upper atmosphere, or arrives just as another body is also passing by. That interaction, that extra pull or drag, is enough to steal just enough energy from the asteroid that it can't escape. Instead of swinging past and continuing on its journey around the sun, it finds itself captured, now orbiting the planet in a long, eccentric ellipse. It's a cosmic kidnapping, in a sense, though one governed by the impartial laws of physics. Neptune's great moon Triton tells this story. It orbits backward retrograde. Astronomers call it opposite to Neptune's rotation. This is nearly impossible if Triton formed with Neptune. It would be like a child on a merry-go-round trying to run backward against the spin. The only explanation is that Triton was once an independent world, probably a dwarf planet from the Kuiper belt, minding its own business in the outer solar system until Neptune's gravity reached out and claimed it. But capture is a violent process, even when no collision occurs. When Triton arrived, Neptune probably had other moons, ones that had been there since the planet's formation. Triton's gravity would have disturbed them terribly. Some would have been flung out into space. Others might have collided with each other or crashed into Neptune itself. It would have been a time of chaos in Neptune's skies, moons appearing and disappearing, orbits shifting and crossing. Eventually, things settled down, but the scars remain. Neptune's moon system is still strange and irregular, with small moons in tilted, eccentric orbits, the survivors and fragments of that ancient disruption. Mars shows us another face of capture. Its two tiny moons, Phobos and Deimos, look like asteroids, potato-shaped, cratered, only a few dozen kilometers across. For a long time, astronomers assumed they were captured asteroids, perhaps snared from the nearby asteroid belt. But their orbits are puzzling, nearly circular, right above Mars's equator. That's too tidy for a typical capture. Some scientists now think Mars might have had a larger moon that was destroyed by an impact, creating a debris ring. Phobos and Deimos would then be not captured strangers but the last remnants of that ring, slowly accumulated from the debris of their predecessor. You see, the formation of moons is rarely simple or clean. Even our own moon, born from that ancient impact, might not have been alone at first. Those computer simulations I mentioned sometimes show multiple large fragments forming from the impact debris. Most merge quickly with the main moon, but some scenarios suggest a second, smaller moon could have survived for millions of years, perhaps a third the size of our current moon, orbiting at a special gravitational balance point. Eventually, this second moon would have grown unstable. The constant pull of Earth's gravity, the subtle influence of the sun, the gentle but persistent tidal forces all would conspire to disturb its orbit. And then, in slow motion over thousands of years, it would spiral inward, not toward Earth, but toward its larger sibling. The collision would be gentle by cosmic standards, the smaller moon essentially plopping onto the larger one at only a few kilometers per second. This could explain one of the moon's great mysteries, why its far side is so different from its near side, with thicker crust and higher terrain. Perhaps it's wearing the remains of a sibling, a second moon that came home to rest. What fascinates me about all these mechanisms, impact, co-formation, capture, is that they're still possible. They're not confined to the ancient past. An asteroid could be captured by Earth tomorrow, giving us a second moon, albeit a tiny one. A large enough impact could, in principle, create a new moon, though we should be grateful such events are vanishingly rare. The universe hasn't stopped making and unmaking moons. We just live in a relatively quiet time. There's something else to consider about how moons form, something that touches on the very nature of gravity and chance. Every moon that exists represents a kind of cosmic lottery win. For every moon that forms and survives, countless potential moons never quite made it. They were the particles in the disk that fell back to the planet or escaped to space. They were the asteroids that flew by just a little too fast to be captured. They were the moonlets that collided and destroyed each other rather than merging successfully. Our moon, singular and serene in our sky, is the winner of all these contests. It gathered more mass than its early competitors. It found a stable orbit that has lasted billions of years. It avoided being shattered by large impacts, though its face shows the scars of many attempts. In a universe of endless possibilities, our particular Earth-Moon system is the one that actually occurred. And this brings us back to our central question, drifting just beneath the surface like the moon behind clouds. If moons can form in so many ways, if the early Earth might have had multiple moons that merged, if capture can happen at any time, then perhaps Earth has indeed had more than one moon. Perhaps we've had many moons over the eons, temporary companions that stayed for a while before moving on or merging with our permanent partner. The evidence for these lost moons might be subtle, a peculiarity in the moon's orbit, an unusual composition in its rocks, the faint capture of tiny asteroids even today. To search for these signs, to piece together the real history of Earth's moons, we need to look more carefully at what we have and what we've lost. We need to read the record written in orbital mechanics and isotope ratios, in the moon's battered highlands and Earth's ancient rocks. The next time you look up at the moon, remember that you're seeing not just a celestial body, but a survivor, possibly the last of its kind, carrying in its very substance the story of tremendous forces and patient accumulation, of worlds colliding, and gravity's gentle insistence that some things are meant to be together. The moon we see tonight might be alone now, but its story, the story of how moons form, suggests that solitude might be the exception rather than the rule. In the vast span of Earth's history, under different skies and above different seas, other moons might have risen and set, their light now lost to time, but their ghosts perhaps still echoing in the moon that remains. The moon we see tonight might be alone now, but its story, the story of how moons form, suggests that solitude might be the exception rather than the rule. In the vast span of Earth's history, under different skies and above different seas, other moons might have risen and set, their light now lost to time, but their ghosts perhaps still echoing in the moon that remains. And if we look carefully, if we know where to search, we might find evidence that Earth has indeed known other moons. Let me take you first to a discovery that might surprise you. Right now, as you listen to these words, Earth probably has more than one moon. Not the large, bright companion we know, but tiny visitors, asteroids no bigger than a car or a washing machine, caught temporarily in Earth's gravitational embrace. We call them mini-moons, and they're real. Picture one of these small wanderers, perhaps a chunk of rock that's been drifting through the solar system for millions of years. It approaches Earth, not on a collision course, but at just the right angle, just the right speed. Earth's gravity reaches out and gently captures it, pulling it into a loose, looping orbit. For a few months, maybe a few years, this little asteroid becomes Earth's second moon. You wouldn't see it with your naked eye. It would be far too small and faint. But it's there, circling our planet in the darkness. In 2020, astronomers discovered one of these temporary companions. They called it 2020 CD3, and it was about the size of a large car. For nearly 3 years, it had been Earth's second moon, quietly orbiting our planet while we went about our lives below, unaware of our extra companion. When they traced back its orbit, they realized it had arrived sometime around 2017, captured from its path around the Sun. And then, in March 2020, it left us, pulled back into solar orbit by the combined gravitational tugs of Earth and Sun. This wasn't the first mini-moon we've found, and it won't be the last. Another one, called 2006 RHUN20, visited us for about a year from 2006 to 2007. And here's what's remarkable. New research suggests that Earth might have half a dozen of these mini-moons at any given time. They come and go like cosmic house guests, staying for a while before continuing on their journey through the solar system. Earth, it seems, is never truly alone. But these mini-moons, fascinating as they are just temporary visitors. What about evidence of more permanent second moons in Earth's past? For that, we need to look not at Earth, but at the moon itself, and at one of its greatest mysteries. Have you ever wondered why the moon looks so different on its two sides? The near side, the face we see, is relatively smooth, covered with those dark maria, the seas of frozen lava that form the features of the man in the moon. But the far side, the face that's always turned away from us, is completely different. It's mountainous, heavily cratered, with a crust that's much thicker, in some places 30 miles thicker than the near side. It's as if the moon is wearing a thick shell on its back. In 2011, a team of scientists proposed a remarkable explanation. What if, they asked, the moon's lopsided appearance is evidence that Earth once had two moons? Their hypothesis goes like this. When that ancient collision between Earth and Theia created our moon, it might not have created just one moon. The debris disk might have spawned two moons, or even several. Computer simulations show this is possible, even likely. Most would have quickly merged with the growing primary moon, but one might have survived longer. Imagine this second moon, perhaps a third the size of our current moon, still enormous by the standards of the mini-moons we catch today. For millions of years, it might have orbited Earth alongside its larger sibling. Perhaps it occupied what we call a Trojan point, one of those special positions where gravitational forces balance, keeping it either 60 degrees ahead or 60 degrees behind the main moon in its orbit. Can you picture that ancient sky? 2 moons rising, 2 moons setting. The larger one bright and familiar, the smaller one perhaps a third as bright, racing through its own cycle of phases. When both were full, the night would have been brilliant. When both were new, the darkness would have been absolute, and sometimes perhaps they would have eclipsed each other, one moon casting its shadow on the other. But this arrangement couldn't last forever. The gravitational dance of 2 moons is inherently unstable. Small perturbations from the sun's gravity, from Earth's slightly irregular shape, would have gradually destabilized the smaller moon's orbit. And then, over thousands of years, something remarkable would have happened. The 2 moons would have begun to converge. This wouldn't have been a violent collision like the impact that created them. By this time, both moons would have been solid, cooled from their molten birth. And their relative velocity would have been small, perhaps just a kilometer or 2 per second, walking speed on a cosmic scale. The smaller moon would have approached its larger sibling slowly, almost gently, and then it would have hit. Scientists call this the Big Splat hypothesis, and the name captures something essential about what would have happened. The smaller moon wouldn't have blasted a crater in the larger one. Instead, it would have splattered against it, like a ball of mud thrown against a wall. Its material would have spread out across one hemisphere of the moon, adding an extra layer of crust, creating highlands and mountains. And perhaps, just perhaps, this is exactly what we see when we look at the moon's far side. Those highlands, that thick crust, might be the remains of Earth's second moon, plastered across the back of the first. It's a hypothesis that's difficult to prove definitively, but it explains so much. The moon's asymmetry, the composition of the far side highlands, even some peculiarities in the moon's orbit. Think about what this means. Every time you look at the moon, you might be seeing not one moon but 2, one still whole, the other merged with it billions of years ago. The moon in our sky might be an amalgam, a fusion of 2 ancient siblings that once danced separately around the Earth. But the evidence for Earth's lost moons doesn't end with ancient history. There's another kind of companion that Earth has, one that exists in a strange borderland between being a moon and not being a moon. I'm speaking of the Kordylowski clouds, and they're unlike anything else in the Earth-Moon system. To understand these clouds, you need to understand something about gravity and balance. In any system where one body orbits another, like the moon orbiting Earth, there are 5 special points where the gravitational forces balance perfectly. We call these Lagrange points, after the mathematician who discovered them. At these points, an object can remain stationary relative to the 2 larger bodies, held in place by the balance of forces. 2 of these points, called L4 and L5, lie along the moon's orbit, one 60 degrees ahead of the moon and one 60 degrees behind. And at these points, something strange has accumulated. Vast clouds of dust, first photographed by the Polish astronomer Kazimierz Kordylewski in 1961. These clouds are enormous, tens of thousands of miles across, but so faint that they're invisible to the naked eye. You need special filters, special techniques to see them at all. What are these clouds? They're cosmic dust, accumulated over millions of years. Some of it might be debris from asteroid impacts on the moon, tiny fragments blasted into space and trapped at these balance points. Some might be interplanetary dust, wandering through the solar system until Earth's and Moon's gravity captured it. The clouds are constantly changing, gaining new particles. losing others. But they persist. Ghost moons made of dust rather than rock. In the right light, with the right equipment, you can photograph them, these faint, glowing clouds that share the moon's orbit. They're not moons in any conventional sense, but they are companions to Earth, and they've probably been there for millions of years. Some have even called them Earth's ghost moons, and there's something poetic about that. These ethereal clouds of dust, barely there, haunting the gravitational balance points of our system. And then there are the quasi-satellites, objects that seem to orbit Earth but don't. Not really. The most famous of these has the beautiful name Kamo'oalewa, after a Hawaiian word that refers to an oscillating celestial object. Kamo'oalewa is an asteroid about the size of a Ferris wheel, and it's been Earth's companion for at least a century, possibly much longer. Here's the strange thing about Kamo'oalewa. It appears to orbit Earth, but it actually orbits the Sun. It's just that its orbit is synchronized with Earth's in such a way that it seems to loop around us. From Earth's perspective, it traces a peculiar path, sometimes ahead of us, sometimes behind, sometimes above Earth's orbital plane, sometimes below. It's like a cosmic dance partner, maintaining a careful distance never closer than about 14 million kilometers, never farther than about 40 million. But here's where the story gets even more interesting. When scientists analyzed the light reflected from Kamo'oalewa, they found something unexpected. Its spectrum, its color signature matches the moon's. Not just similar, but remarkably close. This tiny asteroid appears to be made of lunar material. It might be a fragment of the moon itself, blasted into space by an ancient impact, and now orbiting near Earth, a small piece of our moon that became, in a sense, a separate moon. Think about that for a moment. A piece of the moon, orbiting independently, yet still tied to Earth. It's been suggested that Kamo'oalewa might have been created by the same impact that formed Giordano Bruno crater on the moon, an event that might have occurred within recorded human history, perhaps in 1178, when monks in Canterbury recorded seeing a strange explosion on the moon. If true, this would mean that humans actually witnessed the birth of a new quasi-moon, though they couldn't have known what they were seeing. And this brings us back to our central question, doesn't it? Has Earth had more than one moon? The answer, we're discovering, is both yes and no, both simple and complex. Yes, Earth captures temporary moons all the time. Yes, Earth might have had a substantial second moon billions of years ago. Yes, Earth has dust clouds and quasi-satellites that are, in their own ways, additional moons. But there's more evidence to consider, evidence written in gravity itself. The moon's orbit today is tilted about 5 degrees to Earth's orbital plane around the sun. That might not sound like much, but it's actually puzzling. Models of the moon's formation suggest it should have formed with a steeper tilt, perhaps 10 degrees or more. Something must have changed it. One possibility is gravitational interactions with additional moonlets in Earth's early history. If Earth had multiple moons after the giant impact, even temporarily, their gravitational tugs on each other could have altered their orbits. As these moonlets merged or were lost, they would have left their mark on the surviving moon's orbit. That 5-degree tilt we see today might be a fossil, a gravitational memory of moons that no longer exist. There's something deeply moving about this search for lost moons. Every piece of evidence we find, every captured asteroid, every orbital peculiarity, every asymmetry in the moon's structure, tells us that the neat, simple story of one Earth, one moon is more complex than we imagined. Earth's gravitational reach extends far beyond what we can see, catching and releasing small moons, perhaps once embracing larger ones. I want you to imagine standing on Earth 4 billion years ago, looking up at a sky with 2 moons. The larger one, still glowing with the heat of its formation, its surface an ocean of magma slowly cooling and crystallizing. The smaller one, perhaps already solid, racing through its faster orbit. Both would have been much closer than the moon is now, looming huge in the sky. The tides they raised would have been monstrous, hundreds of meters high, sweeping across the young Earth's surface. And then, over millions of years, you would have watched them slowly converge. Not dramatically, not suddenly, but gradually, inevitably. Night after night, year after year, the gap between them shrinking until finally, in a slow-motion collision that might have taken hours, they merged. The smaller moon spreading across the larger one's surface like thick paint, creating the highlands we still see today. That merger, if it happened, would have been visible from Earth. Any life that existed then, probably nothing more than microbes in the ocean, wouldn't have been aware of it. But the event would have changed the tides, changed the length of Earth's day, changed the night sky forever. Two moons became one, and Earth settled into the single moon system we know today. Or did it? Because the evidence suggests that Earth's relationship with its moons past, present, and future is dynamic, constantly changing. We catch new mini-moons and lose them. Quasi-satellites dance around us for centuries, then drift away. The Kordylewski clouds persist at their Lagrange points, neither fully moons nor fully not moons. And our one large moon continues its slow journey outward, 3.5 centimeters farther away each year, carrying perhaps within its very structure the remains of a sibling from the dawn of the solar system. The search for Earth's lost moons is really a search for Earth's story, for the complex truth of how our planet and its companions have evolved together over billions of years. And what we're finding is that the truth is far stranger, far more beautiful than the simple picture we once imagined. Earth has had many moons, in many forms, coming and going like actors on a cosmic stage. Some stayed for billions of years, some for just a few months. Some were rock and ice, some were merely dust and dreams. When you next look at the moon, remember this: you're looking at a survivor, possibly the last of many moons that once circled Earth. Its scarred face, its lopsided structure, its slowly evolving orbit. All of these are clues to a history we're only beginning to understand. The moon we see is alone now, but it carries within it the memory of companions lost to time, merged or scattered, leaving only subtle traces of their existence. The evidence of Earth's lost moons is all around us, if we know how to look. It's in the mini-moons that visit us briefly. It's in the dust clouds at the Lagrange points. It's in the quasi-satellites that dance around us. It's in the moon's own asymmetric structure and tilted orbit. Each piece of evidence is like a whisper from the past, telling us that Earth's story is more complex, more dynamic, more wonderful than we ever imagined. And perhaps that's the most profound truth we're uncovering, that change is the only constant in the cosmic dance. Moons come and go, orbits evolve. What seems permanent on human timescales is transient on cosmic ones. The moon that lights our nights tonight is not the moon that lit the nights of the dinosaurs, and it's not the moon that will light the nights of whatever comes after us. It's a moon in motion, in transition, carrying the history of all Earth's moons within its ancient, battered surface. These lost moons of Earth aren't really lost at all. They're transformed, merged, scattered, but still present in the gravitational rhythms of our world, in the tides that rise and fall, in the slow dance of celestial mechanics that continues even now, adding new chapters to a story that began 4.5 billion years ago and shows no sign of ending. These lost moons of Earth aren't really lost at all. They're transformed, merged, scattered, but still present in the gravitational rhythms of our world, in the tides that rise and fall, in the slow dance of celestial mechanics that continues even now, adding new chapters to a story that began 4.5 billion years ago and shows no sign of ending. And so we arrive at one of the most extraordinary chapters in this story, a time when the moon hung so close to Earth that it dominated the sky like a second sun, when days passed in the span of heartbeats, and when the very foundations of life were being laid down in waters stirred by tides we can barely imagine. To understand what Earth might have been like with multiple moons, we need to travel back through deep time to an era when our single moon was younger, fiercer, and far more intimate with our planet than it is today. Picture, if you will, standing on the shores of an ancient Earth 3.5 billion years ago. The sun above you is dimmer than the one we know, perhaps 25% weaker, casting a pale yellow light across waters that have never known the touch of oxygen. But look up, and there in the sky hangs something that would stop your breath if you had lungs to breathe with. The moon, our moon, spans perhaps 10 degrees of sky, 20 times wider than it appears to us now. It's not the cool, distant pearl we see tonight. This moon is a presence, a weight in the heavens, its surface still glowing faintly in places where recent impacts have exposed the molten rock beneath its cooling crust. You're standing in a day that lasts perhaps 12 hours from sunrise to sunrise. The earth beneath your feet is spinning so fast that if you could somehow sense it, you'd feel the centrifugal force pulling you gently outward, making you imperceptibly lighter than you would be in our time. And this rapid spin isn't just about shorter days. It's reshaping everything about this young planet's behavior, from the patterns of its winds to the mixing of its oceans. Let me take you even further back to the very beginning of this story. 4.5 billion years ago, in the immediate aftermath of the great collision that birthed the moon, our satellite hung perhaps only 19,000 kilometers above Earth's surface. Can you imagine it? At that distance, just 1.5 times Earth's own diameter, the moon would have filled 30 degrees of sky or more. It would have been not just visible but overwhelming, a constant companion that never truly set, racing around Earth every few hours in a cosmic dance so tight and fast it would have made the heavens themselves seem to spin. In those earliest days, Earth itself was rotating frantically, completing a full turn in perhaps 5 or 6 hours. The combination of this rapid spin and the moon's proximity created a world we would barely recognize. Winds, driven by the Coriolis effect of that swift rotation, would have carved the atmosphere into dozens of narrow circulation cells, each spawning its own weather patterns. Storms would have been smaller but more numerous, whipping around the planet in tight spirals that formed and dissipated in what we would consider minutes rather than days. And that brings us back to our question: what if Earth had possessed not one but 2 moons during these ancient eras? The evidence suggests it's not merely possible, but perhaps even likely that for some period after the Great Impact, multiple moonlets condensed from the ring of debris that circled our newborn world. Computer simulations of that cosmic collision show that the debris disk thrown into orbit was massive enough and complex enough that several moons could have initially formed, each carving its own path through the glowing remnants of the impact. Imagine then, in those first few million years, looking up at a sky with 2 or perhaps even 3 moons. The largest, what would become our moon, already beginning to dominate, but accompanied by smaller siblings, each perhaps a few hundred kilometers across. These lesser moons wouldn't have lasted long on cosmic timescales. The gravitational dynamics of such a system are inherently unstable. The larger moon's gravity would have gradually perturbed the orbits of its smaller companions, either sending them crashing back to Earth in spectacular impacts that would have added new scars to our planet's already battered surface, or causing them to spiral outward until they escaped Earth's grip entirely, becoming orphan worlds circling the sun. But while they lasted, perhaps a few million years, perhaps longer, these multiple moons would have created a symphony of tides unlike anything our planet has experienced since. If you've ever stood at the shore and watched the tide come in, you know the power of our single moon's pull. Now multiply that effect, add the complex interference patterns of 2 or 3 gravitational sources, each pulling the oceans in its own rhythm. The mathematics of such a system are beautifully complex. With our moon alone at its ancient closer distance, tides would have been perhaps 1,000 times stronger than today. Ocean waters wouldn't have gently risen and fallen. They would have surged across the landscape in walls hundreds of meters high. Add a second moon, perhaps half the size of the first, and orbiting at a different distance, and these already massive tides would have become chaotic. Sometimes the moons would align, their gravitational pulls combining to create supertides that could have swept across entire continents. At other times, they would work against each other, creating complex patterns of highs and lows, currents and countercurrents that would have turned the oceans into a constantly churning cauldron. These ancient tides did more than just move water. They were engines of change, grinding away at the newly formed continents, carrying minerals and nutrients from the land into the sea. In the tidal zones, those areas alternately submerged and exposed, unique chemical reactions would have taken place, perhaps contributing to the complex chemistry that would eventually give rise to life. Some scientists speculate that these extreme tidal cycles, with their constant mixing and concentrating of chemical compounds in tidal pools, might have been crucial laboratories for the formation of the first self-replicating molecules. The solid Earth itself would have flexed under these massive tidal forces. Today, our planet's crust rises and falls by perhaps 30 centimeters as the moon passes overhead, a motion so subtle we need sensitive instruments to detect it. But with the moon at 1/10 of its current distance, the solid ground would have heaved up and down by meters with each passage. Add a second moon to this equation, and the very rocks would have groaned and cracked under the constantly changing stresses. This flexing would have generated heat through friction, adding to Earth's internal warmth and perhaps driving increased volcanic activity. Imagine a world where the ground itself breathes with the passage of the moons, where mountains crack and heal in rhythm with the sky. As the eons passed, and we're talking about spans of time that dwarf all of human history, periods where 1,000,000 years passes like a season, these moons would have gradually migrated outward. The same tidal forces that flexed Earth's crust also slowly pushed the moons away, converting Earth's rotational energy into orbital energy. But here's where having multiple moons becomes particularly interesting. They wouldn't have migrated at the same rate. The closer moon would have felt stronger tidal effects and moved outward faster. The further moon, experiencing weaker tidal forces, would have migrated more slowly. This differential migration would have led to a cosmic dance of changing relationships. Perhaps initially the moons orbited in a stable resonance, one completing 2 orbits for every 3 of the other, their gravitational tugs keeping them locked in a mathematical harmony. But as they slowly drifted apart at different rates, this resonance would have broken down. The moons might have entered a period of chaotic interaction, their orbits becoming increasingly eccentric, increasingly unpredictable. And this is where the story becomes particularly poignant. Mathematical models suggest that in most scenarios with multiple moons of significant size, the system eventually becomes unstable. The moons begin to perturb each other's orbits more and more strongly. They might swap positions, the inner moon becoming the outer, and vice versa, or their orbits might become so eccentric that they begin to cross paths, and eventually, inevitably, they would either collide or one would be ejected from the system entirely. There's evidence that something like this might actually have happened. Our moon today has a puzzling asymmetry. The near side that faces Earth is relatively smooth and flat, covered with dark basaltic plains we call maria. But the far side is dramatically different, mountainous and heavily cratered, with a crust that's significantly thicker. Some scientists have proposed that this asymmetry is the ghost of a second moon, a smaller companion that orbited Earth for millions of years before finally, gently, catastrophically merging with its larger sibling. Picture that moment, if you can. Not a high-speed collision like the impact that formed the moons, but a slow-motion merger, the smaller moon gradually spiraling inward until it finally made contact with its companion. At the low relative speeds involved, the smaller moon wouldn't have blasted a crater. Instead, it would have pancaked across one hemisphere of the larger moon, adding its mass like a thick blanket of rock. The mountains of the lunar far side might be the remains of Earth's second moon, preserved for billions of years like a fossil in stone. During the era when Earth might have possessed multiple moons, life was just beginning its tentative emergence. The first cells, simple bags of chemistry capable of reproducing themselves, were appearing in the warm, mineral-rich waters of the ancient oceans. These early organisms would have been profoundly influenced by the rhythms of the moons. Even today, many marine species time their reproduction to the lunar cycle, releasing eggs and sperm when the full moon creates the highest tides. How much more intense would this coupling have been when the tides were massive and multiple moons created complex patterns of light and gravity? I want you to imagine those ancient nights, lit by multiple moons in different phases. Perhaps the larger moon is full, casting shadows sharp enough to read by if there had been anyone to read, while a smaller moon shows only a crescent, adding its own subtle light to the scene. The patterns of moonlight on the water would have been endlessly complex, shifting and changing as the moons pursued their separate paths across the sky. For any primitive organisms capable of detecting light, these patterns might have provided the first calendars, the first way of marking time beyond the simple cycle of day and night. The influence of these ancient moons extended beyond Earth itself. The same tidal heating that warmed Earth's interior would have affected the moons as well. A smaller companion moon, subjected to the constantly changing gravitational stresses of orbiting between Earth and a larger moon, might have remained geologically active far longer than it would have in isolation. Perhaps it developed its own volcanic activity, spewing fountains of molten rock into the vacuum that would have been visible from Earth as glowing spots on the moon's surface. Imagine looking up at night and seeing not one but two moons, one of them occasionally flaring with volcanic light like a distant ember in the sky. As we move forward through deep time, though still billions of years in our past, the picture slowly transforms. The hypothetical second moon is gone, either merged with the first or lost to space. Our single remaining moon continues its slow journey outward, and Earth's rotation gradually slows. By 2 billion years ago, the moon has receded to perhaps 2/3 of its current distance. Days have lengthened to maybe 18 hours. The tides, while still stronger than today's, have calmed from their primordial fury to something more recognizable. Life, meanwhile, has grown more complex. The first cells with nuclei have appeared, and some have begun to cooperate, forming the earliest multicellular organisms. These creatures live in a world still profoundly shaped by the moon's proximity. The stronger tides create vast intertidal zones, areas that are underwater at high tide and exposed at low tide. These zones are crucibles of evolution, challenging life to adapt to constantly changing conditions. Perhaps it's here, in these moon-stirred margins between land and sea, that some organisms first developed the ability to survive out of water, taking the first tentative steps toward colonizing the land. The fossil record from this era preserves hints of the moon's influence. Certain types of sedimentary rocks called tidal rhythmites preserve the daily and monthly patterns of ancient tides in their layers, like tree rings recording the passage of years. By counting these layers, scientists can determine how many days were in an ancient month, how many months in a year. And what they find confirms our story. The further back in time we look, the more days there were in a year, the closer the moon must have been. By the time we reach the Cambrian explosion, that great flowering of complex life around 540 million years ago, the moon has retreated to about 95% of its current distance. Days last perhaps 21 hours. The tides are still notably stronger than today's, but they follow patterns we would recognize. Yet even at this late date, the moon's influence on life remains profound. Many of the creatures that emerged during this period show evidence of tidal adaptations: shells that can close tight to preserve moisture, methods of anchoring to rocks to resist the pull of waves, behaviors timed to the cycle of the tides. And what if a second moon had survived to this era? How different might the Cambrian explosion have been? Perhaps the complex tidal patterns created by two moons would have created more diverse ecological niches, spurring even greater evolutionary innovation. Or perhaps the chaos of unpredictable tides would have made the transition from sea to land more difficult, delaying the colonization of the continents. We can only speculate, but it's fascinating to consider how the presence or absence of a second moon might have changed the entire trajectory of life on Earth. As we approach more recent geological time, the last few 100 million years, the Earth-Moon system has settled into something close to its modern configuration. The Moon continues to recede at its stately pace of 3.8 centimeters per year, a rate so slow that human civilizations have risen and fallen without noticing any change. Days have lengthened to very nearly 24 hours, though they continue to grow imperceptibly longer in another 200 million years. A day might last 25 hours. But even in this relatively stable period, there are hints of what might have been. Computer simulations suggest that Earth occasionally captures small asteroids into temporary orbits, creating brief periods when we technically have two moons. These captured objects are tiny, usually just a few meters across, and their orbits are unstable, lasting at most a few years before they escape back into solar orbit. But they remind us that the potential for multiple moons is always there, lurking in the complex dynamics of orbital mechanics. There's something profound about looking back through deep time at the moon's evolution, seeing how it has shaped and been shaped by its relationship with Earth. The moon we see tonight, serene and distant in our sky, is the same world that once loomed huge and violent above a younger Earth. The gentle tides that lap at our beaches today are the faint echoes of the mountain-high surges that once swept across primordial continents. And somewhere in the moon's battered surface, in the asymmetry between its two faces, might be preserved the memory of a sibling moon that shared the sky billions of years ago. This journey through deep time also reminds us of the extraordinary contingency of our world. The moon's current distance, Earth's 24-hour day, the modest tides that rhythm our coasts, none of these are fixed or inevitable. They're snapshots of an ongoing process, moments in a dance that has been proceeding for billions of years and will continue for billions more. In the far future, as the moon continues to recede, there will come a time when it's too small in the sky to fully eclipse the sun. Further still, the moon might escape Earth's grip entirely, leaving our world truly alone for the first time since its violent birth. But for now, in this moment of cosmic time that we happen to inhabit, we have the perfect moon at the perfect distance. Close enough to stir our oceans and steady our axis, far enough to give us manageable tides and 24-hour days that match our biological rhythms. It's a Goldilocks situation that has helped make Earth the living world we know. And understanding how different things were in deep time, how violent, how chaotic, how magnificent, makes us appreciate the cosmic gift of the moon we have today. As we prepare to leave this ancient Earth and return our thoughts to the present, consider this. Every time you see the moon in the sky, you're looking at deep time made visible. That familiar face has witnessed Earth's entire history, from the formation of the first oceans to the rise of creatures capable of looking back and wondering about their origins. And perhaps, just perhaps, it carries within its rocks the memory of other moons that once shared its sky, ghost companions whose existence we can only infer from the faint clues they left behind in gravity's patient record. As we prepare to leave this ancient earth and return our thoughts to the present, consider this. Every time you see the moon in the sky, you're looking at deep time made visible. That familiar face has witnessed Earth's entire history, from the formation of the first oceans to the rise of creatures capable of looking back and wondering about their origins. And perhaps, just perhaps, it carries within its rocks the memory of other moons that once shared its sky, ghost companions whose existence we can only infer from the faint clues they left behind in gravity's patient record. But Earth is not the only world with moons. In fact, when we look outward into our solar system, we discover that Earth's single large moon makes us something of an outlier. The gas giants beyond Mars are veritable moon factories, each hosting dozens upon dozens of satellites in complex orbital dances that make our simple Earth-Moon system seem almost quaint by comparison. These alien moon systems offer us natural laboratories where we can observe what happens when multiple moons share the same sky, interact gravitationally, and create patterns of motion that would seem like magic to anyone who didn't understand the patient mathematics of orbital mechanics. Let's begin our journey with Jupiter, the king of planets, which until very recently held the title of having the most moons in our solar system. As of this moment in 2025, we know of at least 95 confirmed moons circling this giant world. Most of these are small, irregular bodies, captured asteroids, really, just a few kilometers across, tumbling through space in distant, tilted orbits. But 4 of Jupiter's moons are worlds unto themselves, comparable in size to our own moon, or even larger. These are the Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo over 400 years ago when he first turned his telescope toward Jupiter. They form a miniature solar system around their giant host. Ganymede, the largest, is bigger than the planet Mercury. It's a world of ice and rock with its own magnetic field, the only moon in our solar system known to generate one. If you were somehow floating in Jupiter's cloud tops, where what passes for Jupiter's surface would be, you would see these 4 moons as bright points of light, moving visibly from night to night. Occasionally, one might appear large enough to show as a tiny disk to the naked eye, especially Ganymede or Callisto when they pass closest. But here's where it becomes truly fascinating. From Jupiter itself, the moons wouldn't loom as large as our moon does to us, even though they're substantial worlds. Jupiter is so massive and they orbit relatively far from Jupiter's cloud tops that they appear more like brilliant stars than the disk we're accustomed to seeing. Callisto, for instance, orbits almost 2 million kilometers from Jupiter's center. Yet from the perspective of the moons themselves, the view is nothing short of magnificent. Imagine standing on Io, the innermost of the 4 great moons. Above you, Jupiter would fill a huge portion of the sky, perhaps 40 degrees across, a swirling, banded giant of storms and clouds. Its great red spot like a vast eye gazing down, and you wouldn't be alone in that sky. Europa would appear as a bright sphere, sometimes close enough to see surface features with the naked eye. Ganymede and Callisto would be visible as well, smaller but still prominent, creating a celestial family portrait that would dwarf anything we see from Earth. What makes this system particularly interesting is how these moons interact with each other. Io, Europa, and Ganymede are locked in what astronomers call a orbital resonance, specifically a 1-2-4 resonance. For every orbit Ganymede completes, Europa orbits twice, and Io orbits 4 times. This isn't coincidence. It's a gravitational dance that has evolved over millions of years, with each moon's gravity tugging on the others in a rhythmic pattern that keeps their orbits stable. But this stability comes with a price. The constant gravitational pulling between the moons creates what's called tidal heating. As Io orbits Jupiter, Europa and Ganymede pull it slightly off course, making its orbit more eccentric. This means Io experiences varying tidal forces from Jupiter, sometimes stronger, sometimes weaker, which flex and squeeze the Moon's interior. The friction from this constant kneading heats Io from within, creating the most volcanically active body in our solar system. Hundreds of volcanoes erupt continuously on Io's surface, spewing sulfur compounds that paint the Moon in yellows, oranges, and reds. Europa experiences similar tidal heating, though less extreme. This heating is thought to maintain a liquid ocean beneath Europa's icy crust, an ocean that might contain twice as much water as all of Earth's oceans. Combined, the implications are staggering. Here we have a Moon, warmed not by the distant sun but by the gravitational embrace of its neighbors, potentially harboring conditions suitable for life. It's a powerful reminder that when multiple moons share a system, they don't just coexist, they profoundly influence each other's evolution and possibly their habitability. And this brings us back to our question about Earth. If our planet had two large moons in a similar resonance, we might see comparable effects. Perhaps the moons would lock into a pattern where one orbits twice for every orbit of the other. This could create enhanced tidal stresses not just on Earth but on the moons themselves. One or both might experience enough tidal heating to remain geologically active far longer than our current Moon, which has been essentially dead for billions of years. The visual spectacle would be remarkable too. Jupiter's moons regularly eclipse each other, casting shadows on Jupiter's cloud tops and creating complex patterns of light and shadow. From one moon, you might see another transit across the Sun, or watch as one moon disappears into the shadow of another. If Earth had two moons, we would witness similar celestial choreography, more frequent eclipses, both solar and lunar, and the fascinating sight of one moon eclipsing the other, what we might call a moon-moon eclipse. But let's journey outward to Saturn, which now officially holds the record as the solar system's moon champion. Recent discoveries have brought Saturn's moon count to an astounding 145. Like Jupiter, most of these are tiny captured objects, but Saturn also hosts a remarkable collection of mid-sized icy moons and one true giant, Titan. Titan is extraordinary. At over 5,000 kilometers across, it's larger than Mercury and the only moon in our solar system with a thick atmosphere. If you stood on Titan's surface under its orange hazy sky, Saturn would loom 11 times larger than our moon appears from Earth. The weak sunlight filtering through Titan's atmosphere would cast everything in a perpetual twilight, and you might see methane rain falling from clouds onto lakes of liquid hydrocarbons. Other moons, Enceladus, Mimas, Tethys, would appear as points of light, some bright enough to cast faint shadows. Saturn's moon system demonstrates something else important. Moons can influence more than just each other. Within Saturn's magnificent rings orbit tiny moonlets like Daphnis and Pan. These shepherding moons, despite being only a few kilometers across, create visible waves and gaps in the rings through their gravitational influence. It's a visible demonstration of how even small moons can have system-wide effects. Several of Saturn's moons are also locked in orbital resonances, just like Jupiter's. Enceladus and Dione share a 1:2 resonance that helps keep Enceladus's orbit slightly eccentric. This eccentricity, combined with tidal heating from Saturn, powers the spectacular geysers that erupt from Enceladus's south pole, spraying water ice into space and actually contributing material to one of Saturn's rings. It's another example of how the interaction between multiple moons can create unexpected phenomena. Saturn's moon system even features what are called co-orbital moons, Janus and Epimetheus, which share nearly the same orbit and periodically swap positions in an intricate celestial dance. Every 4 years, the inner moon catches up to the outer one, and their mutual gravity causes them to exchange places. If Earth had developed such a co-orbital arrangement with a second moon, Imagine the confusion and wonder of ancient astronomers watching as two moons regularly traded positions in the sky. There's also a darker story written in Saturn's moons. The irregular moons, those in distant, tilted, often retrograde orbits, tend to cluster in groups with similar orbital characteristics. This clustering suggests they're fragments of larger moons that were destroyed, possibly by collisions. Scientists believe a moderate-sized moon may have shattered around Saturn as recently as 100 million years ago, spawning dozens of the small moons we see today. This is sobering when we think about Earth with multiple moons. Having more than one moon isn't necessarily a stable, permanent arrangement. Moons can collide, be torn apart by tidal forces, or disrupt each other's orbits catastrophically. If Earth had gained a second moon in an unfortunate orbit, it might have suffered a similar fate, either colliding with our moon or being broken apart, possibly creating a temporary ring system around Earth. Now let's turn our gaze to the ice giants at the edge of our solar system. Uranus, tilted on its side like a cosmic bowling ball, has 27 known moons. What makes Uranus unique is that its moons orbit around its equator, which means they're also tilted nearly perpendicular to the plane of the solar system. During Uranus's long seasons, each lasting 21 Earth years, the moons can experience extreme variations in sunlight. At the solstices, the moons essentially orbit over the planet's poles, spending half their orbit in constant sunlight and half in darkness. The largest moons of Uranus, Titania, and Oberon are about 1/5 the size of our moon. If Earth's axis were tilted like Uranus's, and if we had multiple moons, their dance across our sky would be unlike anything we can imagine. Sometimes they would arc overhead from east to west, sometimes they would circle around the horizon, and at certain times of year, they might hang nearly motionless in the sky for hours as they orbited edge-on to our perspective. Neptune, the outermost of the giant planets, offers perhaps the most dramatic cautionary tale about multiple moons. Neptune has 14 known moons, but its system is dominated by one giant, Triton. Triton is unusual because it orbits backward, retrograde to Neptune's rotation. This is a telltale sign that Triton wasn't formed with Neptune but was captured, probably from the Kuiper belt where Pluto resides. When Triton was captured, it would have wreaked havoc on whatever moon system Neptune originally possessed. The gravitational disruption would have been catastrophic. Any moons orbiting close to Neptune would likely have been destroyed or ejected. Some might have collided with each other or with Neptune itself. Others might have been flung out of the system entirely. Today, Neptune's inner moons are all small, irregular bodies that probably formed from the debris of this ancient catastrophe, or were captured later. This is a crucial lesson for our thought experiment about Earth. If our planet were to capture a large second moon, say, something the size of Mars's moon, Phobos or larger, it wouldn't simply slot into a neat orbit alongside our current moon. The gravitational perturbations could destabilize the entire system. Our moon's orbit might become eccentric or inclined. The two moons might enter unstable resonances that would eventually lead to collision or ejection. The relative peace and stability of our single moon system might be shattered, with consequences that could affect Earth's rotation, tides, and even its habitability. Yet there's something beautiful in contemplating these multi-moon worlds. They show us that the cosmos is capable of extraordinary variety and complexity. Where Earth has one large moon in a simple, nearly circular orbit, other worlds juggle dozens of moons in elaborate orbital arrangements. Some moons shepherd rings, others generate magnetic fields, still others harbor hidden oceans or spew volcanic fountains into space. The giant planets also teach us about orbital resonances, those mathematical relationships that can stabilize a system of multiple moons for billions of years. Jupiter's Laplace resonance between Io, Europa, and Ganymede is a kind of gravitational music, with each moon completing its orbit in harmony with the others. These resonances prevent close encounters between moons, keeping them from colliding or disrupting each other's orbits. If Earth had developed two moons that settled into such a resonance, perhaps one moon orbiting twice for every orbit of the other, they might have remained stable for the path. Entire history of our planet. The pattern of tides would have been more complex but predictable. Ancient astronomers might have discovered the mathematical relationship and seen in it evidence of divine harmony. Our calendars, mythology, and even our mathematics might have developed differently as we tried to track and understand the dance of two moons. Let me paint you a picture of what Earth's sky might have looked like with multiple moons, informed by what we see in these other worlds. Imagine two moons of different sizes, one perhaps as large as our current moon, another half its size. The larger moon might orbit close to where our moon is now, taking a month to circle Earth. The smaller moon, closer to Earth, might complete an orbit in just a week or two. On some nights, both moons would be full, flooding the landscape with silver light bright enough to read by, casting double shadows in different directions. Wildlife that depends on darkness would have had to adapt to these brilliant nights. Plants that bloom by moonlight would have more complex cycles to follow. On other nights, you might see the nearer moon pass in front of the farther one, creating a kind of lunar eclipse visible only from Earth. Or perhaps the two moons would appear close together in the sky, like cosmic siblings, slowly drifting apart as the night progressed. Occasionally, both moons might be new at the same time, plunging the night into a darkness we rarely experience now with our single moon. The tides would tell their own complex story. Instead of the relatively simple pattern we know, 2 high tides and 2 low tides each day, we might see interference patterns as the gravitational pulls of the two moons. Sometimes reinforced each other, and sometimes cancelled out. There might be super tides when both moons aligned with the sun, and peculiar still water days when their pulls exactly counteracted each other. But perhaps most importantly, looking at these other worlds reminds us that our moon, singular, large and stabilizing, is actually quite special. Most rocky planets don't have such large moons. Mercury and Venus have none at all. Mars has 2, but they're tiny captured asteroids that have minimal effect on their planet. Earth's moon is unique in the inner solar system, and that uniqueness has shaped our planet's evolution in profound ways. When we see Jupiter's volcanic Io heated by tidal forces from its fellow moons, we can appreciate that our moon's gentle tidal heating of Earth has been just right, enough to contribute to plate tectonics and ocean mixing, but not so much as to make our planet uninhabitable. When we see the complex, often unstable arrangements of captured moons around the outer planets, we can be grateful that our moon formed from a giant impact, giving us a large, stable companion rather than a collection of small, chaotically orbiting bodies. These other worlds also show us what we're missing, aesthetically speaking. The photographs sent back from the Cassini spacecraft of Saturn's moons, with the giant planet and its rings as backdrop, are among the most beautiful images ever captured. Jupiter's moons creating shadows on the planet's cloud tops or eclipsing each other in complex patterns would be magnificent to witness. If Earth had multiple moons, our sky would offer its own spectacular shows, different from what we have, neither better nor worse, but undeniably richer in variety. And yet, as I contemplate these busy moon systems of the outer planets, I find myself returning again and again to a simple truth. Sometimes, one is enough. One moon to light our nights and drive our tides. One moon to stabilize our axis and slow our rotation to a comfortable day length. One moon to inspire our stories and mark our months. One moon to be the stepping stone that might one day lead us to the stars. The other planets show us what's possible when worlds collect multiple moons. They demonstrate the complex gravitational choreography that can emerge, the tidal heating that can warm otherwise frozen worlds, the visual splendor of crowded skies. But they also show us the chaos that can ensue, moons colliding, shattering, being captured and ejected. Our single moon, born from violence but settled into peaceful stability, may be exactly what Earth needed to become the living world we know. And that brings us back to our central question: what if a second moon appeared today? Let me paint you a picture of this transformation, slowly, carefully. Imagine waking tomorrow morning, and as you step outside with your coffee, you notice something wrong with the dawn sky. There, hanging beside the setting moon, our familiar moon, is another sphere, not quite as large, perhaps a third the size in appearance, but unmistakably there. Reddish maybe, or pale grey, catching the first light of the sun that hasn't yet crested your horizon. The news would explode within minutes. Every telescope on Earth would swing toward this impossible visitor. Scientists would scramble for explanations, while social media would erupt in a cacophony of wonder and terror. Some would call it divine intervention, others an apocalyptic sign, but beneath all the human noise, the Earth itself would already be responding to this new gravitational partner. The ocean would feel it first. Think about the tides, those gentle, twice-daily rhythms that have shaped our coastlines for billions of years. They rise and fall, perhaps 6 feet, maybe 10 in certain places. Now, imagine if those same waters suddenly had to answer to 2 masters pulling from different directions. If this new moon were closer than our current one, let's say half the distance, the mathematics become staggering. Tidal forces scale with the inverse cube of distance. A moon twice as close doesn't create tides twice as strong. It creates tides 8 times more powerful. Picture the first high tide under this new regime. In New York Harbor, where the tide normally rises 6 feet, the water might surge 30 feet or more. The Hudson River would reverse, not gently but violently, a wall of seawater racing upstream. Venice wouldn't slowly sink, it would drown in hours. The Thames Barrier in London, that marvel of engineering designed to protect the city from storm surges, would be overwhelmed like a child's sandcastle before an unexpected wave. But it wouldn't just be the height of the tides, it would be their complexity. Our moon creates a fairly predictable pattern: high tide, low tide, roughly every 12 hours. With 2 moons pulling from different angles, at different speeds, the ocean would become a chaos of competing forces. Imagine standing on a beach trying to understand when the water would rise or fall. Sometimes the 2 moons would align, creating super tides that would dwarf anything we've known. Other times they'd pull at right angles, creating multiple daily tides of varying heights. The very concept of high tide and low tide might lose meaning in certain places. And these wouldn't be slow, creeping tides like we know. If the second moon orbited quickly, say, once every few days instead of our moon's monthly journey, the tides would race. You might see the ocean rise 20 feet in an hour, then drop just as fast, only to surge again from a different direction as the second moon swung past. I want you to really feel what this means. Stand for a moment at the edge of any coast you know. Maybe it's a peaceful California beach where children play in the surf. Maybe it's the rocky shores of Maine where lobster boats bob in quiet harbors. Now, imagine those places transformed into battlegrounds where the ocean wages war against the land several times each day. Beaches wouldn't slowly erode, they'd be carved away in weeks. Coastal cities wouldn't have time to build seawalls, they'd be planning evacuations. The biological world would reel from this change. Think of all the creatures that time their lives by the moon and tides. Sea turtles that emerge on specific nights to lay their eggs. Suddenly their ancestral beaches would be underwater or stranded far from the sea's reach. Coral that spawn on particular full moon nights would find their chemical signals scrambled by conflicting lunar pulls. Grunion, those remarkable fish that ride the highest tides onto California beaches to spawn, might find no pattern to follow, no rhythm to trust. But the chaos wouldn't stop at the shoreline. These massive tidal forces would flex the Earth itself. Our planet isn't perfectly rigid. It bends and stretches under gravitational stress. Right now, the moon raises a tiny bulge in the solid Earth, maybe a foot high, that travels around the planet. With a second moon, especially a close one, these Earth tides could be much stronger. The crust would groan under the strain. Imagine the ground beneath your feet, literally rising and falling several feet each day. Not earthquakes exactly, but a slow, powerful flexing that never stops. Fault lines already under stress might finally slip. Volcanoes teetering on the edge of eruption might find that final push. The ring of fire around the Pacific could light up with activity as magma chambers feel the squeeze and release of these unprecedented tidal forces. Mount Vesuvius, Mount Fuji, Mount Rainier, sleeping giants might wake. And it's not just the earth and oceans that would change. Look up at the night sky as it would become. Tonight, go outside when the moon is full. Notice how bright it is, bright enough to cast shadows, to read by if your eyes adjust. Now add another moon, perhaps half our moon's size but twice as close. The math is elegant and startling. A moon twice as close appears, 4 times larger in area, and provides 4 times the light per unit of apparent size. Even if smaller, this second moon could easily double or triple the brightness of our night sky. What would this mean? The very concept of night would shift. When both moons were full, the landscape would be bathed in an otherworldly twilight. Not daylight, but something far beyond what we call moonlight now. You could see colors at night, the green of leaves, the red of flowers. Nocturnal animals that depend on darkness would have nowhere to hide. Predators that hunt by sight would have new advantages. Prey that freeze in darkness would be exposed. And think about the human response to this brightness. For all of history, night has been our time of rest, of privacy, of mystery. Crimes happen under cover of darkness. Lovers meet in shadow. Sleep comes when the world goes dark. But with 2 moons cycling through their phases, true darkness might come only a few nights each month. Those rare times when both moons are new. Cities might never have needed to develop streetlights. Our circadian rhythms, evolved over millions of years to the reliable pattern of day and night, would be disrupted. Insomnia might become epidemic, as our bodies struggle to understand when to sleep under skies that never fully darken. The calendar itself would need to be reimagined. Right now, many cultures still measure months by the moon's cycle, roughly 29 days from new to new. Islam follows a purely lunar calendar. Others, like the Hebrew and Chinese calendars, balance lunar months with the solar year. But with 2 moons? Imagine trying to track both cycles. If one moon orbited every 29 days and another every 20, they'd align in phase only every 580 days. New vocabularies would emerge. First moon waxing, second moon full, the night of the double crescent, the dark conjunction when both moons are new. Myths and religions would scramble to make sense of this celestial change. The moon has always been singular in our stories, often feminine, often paired with the masculine sun. But 2 moons? Perhaps one would be seen as benevolent, the other malevolent. Good fortune when the bright moon rises, ill omens when the dark moon dominates. New gods would be born in human imagination. The moon that rose in the east might be the bringer of life, the one that rose in the west, the herald of death. I need you to understand that this wouldn't just be a curiosity in the sky. Every aspect of human life would be touched. Agriculture would need to be completely reimagined. Farmers who plant by the moon would need to learn which moon to follow. Nocturnal pests might thrive in the brighter nights, requiring new strategies for crop protection. The timing of harvests, so often tied to the full moon for its light, would become a complex calculation. Architecture would evolve. Buildings would need to withstand not just the occasional storm surge but regular supertides. Foundations would need to account for ground that flexes daily. Windows might be designed differently when nights are so often bright. Perhaps we'd develop new traditions around the rare, truly dark nights, celebrating them as our ancestors celebrated the full moon. But let me take you deeper into this transformed world. Close your eyes and really imagine a year into this new reality. Coastal cities have been abandoned or transformed into Venice-like canal systems, accepting the water rather than fighting it. New cities have risen inland, beyond the reach of the supertides. Humanity has adapted, as we always do, but at tremendous cost. The shipping industry has been revolutionized. Ports that operate on predictable tides can no longer function normally. Some harbors are accessible only a few hours each day when the chaotic tides align just right. Others have been destroyed entirely. Global trade routes have shifted. The Panama Canal, the Suez Canal, these crucial waterways might be impassable at certain tide configurations. Weather patterns, too, would shift. The moon influences our atmosphere, creating atmospheric tides that affect pressure systems. With two moons, these patterns would become far more complex. The jet stream might wobble differently. Hurricanes, which already respond to tidal forces, might be steered in new directions or intensified in unexpected ways. Meteorology, already an inexact science, would need to account for dual lunar influences on every weather system. And here's something that might not be immediately obvious. The second moon would affect our first moon too. Right now, our moon follows a fairly stable, slowly expanding orbit. But add another massive body to the Earth-Moon system, and suddenly you have what physicists call a three-body problem. The two moons would tug on each other even as they orbit Earth. Their paths would become chaotic in the mathematical sense, tiny changes leading to dramatically different outcomes. At first, this might manifest as subtle variations in the moon's position. Astronomers would notice the moon arriving at certain positions, minutes, then hours off schedule. But over time, years, decades, centuries, these perturbations could accumulate. The two moons might settle into a resonance, their orbits locking into a stable pattern where one orbits twice for every 3 orbits of the other. Or they might not. Let me paint you the worst-case scenario, the fear that would lurk in the back of every scientist's mind. The two moons, pulling on each other orbit after orbit, might slowly spiral toward each other. It wouldn't happen quickly. Celestial mechanics operates on vast timescales. But imagine living with the knowledge that in 1,000 years, or 10,000, the two moons would collide. Think about what that would mean for human psychology. We've always assumed the moon would be there, constant, reliable. Empires might rise and fall, but the moon endures. But with two moons locked in a gravitational dance that mathematics suggests could end in collision, every generation would look up and wonder if they'd be the last to see two moons, or the first to see the aftermath of their collision. A ring of debris around Earth, perhaps, or a single moon reformed from the wreckage of two. The space age would take on new urgency. That second moon, so close and unexpected, would be an irresistible target for exploration. Within years, maybe months, we'd send probes. Where did it come from? What's it made of? Is it a captured asteroid, somehow snared by Earth's gravity? Is it a chunk of Earth itself, somehow lifted into orbit? Or is it something else entirely? Something that challenges our understanding of how solar systems work? Human missions would follow. Imagine the race not just to return to our familiar moon, but to be first to set foot on the new one. The geopolitics would be intense. Who owns this new moon? Can anyone claim it? If it's rich in rare minerals or water ice, it could spark a new kind of gold rush. The second moon might become humanity's first true attempt at colonization beyond Earth, closer than Mars, more accessible than our high moon. But I want to bring you back to the immediate, to the visceral reality of this change. Stand with me on a hill overlooking the ocean. It's 3 months after the second moon appeared. The sun is setting, painting the sky in shades of orange and pink. Our familiar moon is rising in the east, nearly full, casting its ancient light across the landscape. But there, in the south, the new moon is also rising. It's smaller but closer, distinctly reddish from iron oxide on its surface. We've learned that much from spectroscopy. The tide is coming in. But coming in doesn't capture the violence of it. The water isn't creeping up the beach, it's charging, a brown wall of churning foam carrying the debris of what used to be seaside towns. Trees, parts of buildings, boats, all tumbling in the surge. The sound is overwhelming, a roar that you feel in your chest. In 6 hours, this water will retreat just as violently, leaving a wasteland of mud and wreckage, only to return again from a different angle as the second moon passes overhead. Birds that once roosted in the coastal marshes wheel overhead, confused, homeless. Their feeding grounds are gone, submerged, or scoured clean. Migration patterns that have existed for millennia are broken. Some species will adapt, find new ways to live in this chaotic new world. Others won't. The bright double moonlight illuminates a landscape in transition. New rivers are carving themselves as the massive tides push water far inland. Lakes that were fresh water a month ago are now brackish, their ecosystems collapsing. The city below the hill where you stand has been evacuated, its streets flooded, its buildings beginning to crumble under the daily assault of the tides. But humans are gathering, organizing, adapting. Temporary camps are becoming permanent settlements on higher ground. Engineers are working on new kinds of structures that can flex with the earth tides without breaking. Scientists are racing to model the new tidal patterns, to find some predictability in the chaos. And somewhere, perhaps, poets are writing about the beauty of 2 moons reflected in the floodwaters, finding meaning in this cosmic disruption. The night grows brighter as both moons climb higher. It's beautiful in its way, this double moonlight. Colors are visible that night once hid, the purple of wildflowers, the silver of spiderwebs. But it's an alien beauty, one that reminds you with every glance skyward that the world you knew, the world humanity evolved in, is gone. Children born after this day will grow up thinking 2 moons are normal. They'll learn in school about the before times when Earth had only 1 moon, when tides were gentle and predictable, when true darkness came every night. It will seem as remote to them as the ice ages seem to us. They'll develop new myths, new explanations for why Earth was granted or cursed with a second moon. Some will worship it, others will fear it, but all will live in its shadow and light. What strikes me most, as I imagine this scenario, is how it reveals our deep connection to the cosmos. We think of ourselves as separate from space, protected by our atmosphere, living our lives independent of the vast universe beyond. But add 1 more moon, just 1 more ball of rock circling our planet, and everything changes. Our cities flood, our ecosystems collapse and reform. Our very sense of time and light transforms. This is the profound lesson hidden in our question. We are not separate from the cosmos. We are woven into it. The moon we have isn't just a decoration in our sky. It's part of the machinery that makes Earth the living world we know. Every stable orbit, every predictable tide, every dark night and bright full moon has shaped not just our planet, but our evolution, our cultures, our dreams. A second moon wouldn't just change our sky. It would change us. It would force us to reimagine everything from our calendars to our coastlines, from our myths to our mathematics. It would remind us, with every glance upward, that we live in a dynamic universe where change can come suddenly, dramatically, irrevocably. And perhaps that's why this thought experiment captivates us. In imagining a second moon, we're really imagining transformation itself, sudden, imposed, inescapable. We're confronting our assumption that tomorrow will be like today, that the fundamental facts of our world are fixed. A second moon would shatter that assumption as surely as it would shatter our coastal cities. But there's something else here too, something more hopeful. In imagining how we'd respond to a second moon, we're also imagining human resilience and adaptability. Yes, there would be chaos and loss. But there would also be innovation, discovery, new beauty. Children born into a two-moon world wouldn't mourn the loss of dark nights any more than we mourn the loss of the truly dark skies our ancestors knew before. Electric lights. They'd find their own wonders in the dance of two moons, create their own myths and meanings. The philosopher Gaston Bachelard once wrote that we understand the world through our dreams of it. In dreaming of a second moon, we understand better the one we have. We see how perfectly tuned our Earth-Moon system is, how much we depend on its stability, how thoroughly it has shaped everything we are. So as you lie in bed tonight, look out your window at the moon, if you can see it. That solitary, ancient companion, slowly retreating from us at 3 centimeters per year, has been Earth's partner for 4.5 billion years. It was there when life first stirred in the primordial oceans. It pulled the tides that may have nudged our ancestors from sea to land. It has looked down on every human who ever lived, every triumph and tragedy, every birth and death. And for now, for today, tomorrow, for millions of years to come, it remains alone in our sky. One moon, one set of tides, one rhythm of light and darkness that has cradled life on Earth since the beginning. What if a second moon appeared today? The Earth would tremble, the seas would rage, and humanity would face perhaps its greatest challenge. But we would adapt, as we always have. We would find new equilibrium with our new celestial companion, and future generations would look up at their two moons and wonder, perhaps, what it would be like to have only one. For now, though, step outside on the next clear night. Look up at our single moon, that faithful guardian, that cosmic accident that became Earth's greatest blessing. Feel the subtle pull of its gravity, the same force that's been quietly shaping our world for eons. And be grateful for the elegant simplicity of one moon, one loyal companion in our journey around the sun. The profound truth is this: we don't need to imagine a second moon to appreciate the one we have. It's already miraculous enough, this chance collision that gave us exactly the moon we needed, at exactly the right distance, creating exactly the right conditions for the emergence and flourishing of life. In a universe of infinite possibilities, we got the one moon that made us possible. And that, perhaps, is the deepest wonder of all. The profound truth is this: we don't need to imagine a second moon to appreciate the one we have. It's already miraculous enough, this chance collision that gave us exactly the moon we needed, at exactly the right distance, creating exactly the right conditions for the emergence and flourishing of life. In a universe of infinite possibilities, we got the one moon that made us possible. And that, perhaps, is the deepest wonder of all. But let me take you now into another realm entirely, the realm where moons become more than mere celestial mechanics, where they transform into something far older, far deeper, the poetry of moons. Stand with me for a moment under tonight's sky. Look up at that singular disk of light, that eternal companion that has watched over every human who ever lived, every story ever told, every prayer ever whispered into the darkness. Before we had language, before we had fire, we had the moon, and in that silver light, we found our first metaphors, our first gods, our first understanding that we were part of something vast and cyclical and beautiful. The moon speaks a language older than words. It speaks in the pull of blood, in the rhythm of tides, in the ancient dance between light and shadow. Every culture that has ever existed has looked up and seen something different, yet something fundamentally the same. A presence, a power, a promise that darkness is never permanent, that fullness and emptiness are merely phases in an eternal cycle. Think about this. The word lunatic carries within it the entire history of our relationship with the moon. Luna, the Roman goddess who drove her chariot across the night sky, became synonymous with madness because our ancestors believed, perhaps correctly, that the full moon could stir something primal within us. Even now, emergency rooms report more activity during full moons. Police stations brace for stranger calls. Perhaps we are more lunar than we like to admit, our inner tides responding to that ancient pull. In China, the moon holds Chang'e, the goddess who stole the elixir of immortality and floated up to live forever in that pale palace, accompanied only by a jade rabbit who pounds the herbs of eternal life. Look closely at the moon's face on a clear night. Can you see the rabbit? Millions of children across Asia grow up seeing not a man in the moon but a rabbit, industrious and eternal, mixing medicines in the silver light. The Greeks saw Selene, Titaness of the moon, who fell so deeply in love with the mortal shepherd Endymion that she begged Zeus to grant him eternal sleep so she could gaze upon his beauty forever. Every night she would descend to the cave where he slept, covering him with her silver light. Is this not how moonlight feels sometimes? Like being observed by something ancient and loving, something that finds us beautiful in our unconscious vulnerability. But imagine, just imagine, if there had been two moons in our sky all along, how different our mythologies would have been. Perhaps we would have seen them as lovers, eternally chasing each other across the heavens. The bright moon and the dark moon, forever in pursuit, occasionally meeting in spectacular conjunctions that would mark the most sacred nights of the year. Or perhaps siblings, one benevolent, one jealous, their relationship playing out in the phases and dances above us. The Dogon people of Mali have long held that there is a second invisible moon they call Po-Tolo, what we now know as the star Sirius B, invisible to the naked eye. How did they know? Their creation myths speak of beings from the sky who told them of this dark companion. If Earth truly had two visible moons, imagine the complexity of mythology that would have emerged. Dual deities for everything, not just sun and moon, but moon, each with their own domain, their own personality, their own devoted followers. In a two-moon world, would Romeo have compared Juliet to both moons? But soft, what light through yonder window breaks? It is the east, and Juliet is the greater moon, nay, both moons combined. Their radiance merged into one impossible beauty. Would Shakespeare have written of the madness of the double full moon, when both orbs hung pregnant and silver in the sky, driving lovers to ecstasy and madmen to prophecy? Let me tell you about something I find deeply moving. The moon you see tonight is the same moon that Sappho saw as she wrote her fragments of desire on the island of Lesbos. The same moon that Li Bai saw when he wrote of trying to embrace the moon's reflection in the river, a poetic pursuit that legend says led to his drowning, though perhaps he simply became one with that silver light he loved so much. The same moon that guided escaped slaves along the Underground Railroad, that witnessed the first human footprint in lunar dust, that will be there long after the last human voice falls silent. This constancy is its own kind of poetry. In a world where everything changes, where mountains erode and oceans shift and entire civilizations rise and fall, the moon remains. Yes, it recedes from us at the rate fingernails grow, 3.8 centimeters per year, but on a human scale, it is eternal. Your great-great-grandchildren will see essentially the same moon you see tonight. But here's where the poetry becomes almost unbearable in its beauty. The moon is made of earth. That impact 4.5 billion years ago, when Theia slammed into our young planet, it means the moon is literally a piece of us. flung into the sky and made eternal. Every time you look at the moon, you're looking at Earth transformed, Earth transcended, Earth made luminous and distant and perfect. What if we'd had two moons born from that same violent birth, twin children of catastrophe, circling their parent world? Would we have loved them equally? Or would human nature have demanded we choose favorites, the way siblings compete for affection? Perhaps one moon would have been for lovers and one for solitaries, one for planting and one for harvesting, one for birth and one for death. I think about the calendars we would have created, trying to track two different cycles. The Islamic calendar follows our single moon strictly. Imagine the complexity of determining Ramadan if there were two moons to consider. Would we have developed mathematics sooner, trying to predict when both moons would be full, when both would be dark? Those rare nights of double darkness would have been times of terror, surely, or perhaps of the deepest magic, when the stars finally had their chance to shine without competition. Consider the symbolism. The moon has always represented the feminine in most cultures, receptive, cyclical, mysterious. The sun is masculine, direct, constant, overwhelming. But two moons? Perhaps one would have been seen as maiden, one as crone, or one as the conscious mind and one as the unconscious. The possibilities for metaphor double and redouble. In Japanese aesthetics, there's a concept called mono no aware, the pathos of things, the gentle sadness of transience. The moon embodies this perfectly. It waxes and wanes, reminding us that nothing is permanent, that beauty is precious precisely because it changes, because it will one day be gone. Cherry blossoms and moonlight, these are the touchstones of mono no aware. But with two moons, would this aesthetic have developed differently? Perhaps the fact that when one moon waned, the other might be waxing, would have suggested not transience, but eternal renewal, not sadness, but hope. Let me share something that moves me. There's a phrase in Sanskrit, Chandrayana, which means moon-faced, and it's a compliment of the highest order, suggesting that someone's face has the moon's perfect luminous beauty. In a two-moon world, would we have needed two words for two different kinds of beauty? Would lovers have argued over which moon their beloved resembled? The moon has always been the destination of our dreams. Long before we had any hope of reaching it, we imagined what it would be like to go there. Lucian of Samosata, writing in the 2nd century CE, described a journey to the moon in what might be the first work of science fiction. Jules Verne shot his characters there from a giant cannon. Georges Méliès filmed a rocket hitting the moon right in its eye, and the moon's face scowled at the indignity. And then, miraculously, impossibly, we actually went. That's one small step for man, one giant leap for mankind. In that moment, the moon transformed from symbol to place, from dream to destination. Yet somehow, it lost none of its poetry. If anything, knowing that human footprints rest in that airless dust, that human voices have echoed in that silence, makes the moon more poignant, more precious. With two moons, would we have been so eager to reach just one? Or would the presence of two destinations have paralyzed us with choice? Would we have fought wars over which moon to claim first? Or would the double prize have somehow united us, made us see that there was enough wonder for everyone? Here's what strikes me most. Every human culture has moon myths, but they're all different. The Aztecs saw a moon god who was cowardly, who only rose to the sky after the brave sun god had already made the journey. The Aboriginal Australians saw the moon as a man who grew fat, waxing, and then thin, waning, as he gorged and then starved. The Vikings saw the moon being chased by a wolf who would one day devour it, bringing about Ragnarok. Yet for all these differences, there are commonalities. The moon is almost always associated with time, with cycles, with femininity, with water, with madness, with transformation. It's as if the moon speaks to something so fundamental in the human psyche that we can't help but mythologize it, can't help but see ourselves reflected in that pale face. 2 moons would have doubled our opportunities for meaning-making. Every culture would have had to decide, are these moons partners or rivals? Parents or children? Do they love each other or fear each other? The mythology would have been impossibly rich, impossibly complex. But let me return to our single moon, our loyal companion. There's something perfect in its singularity. It needs no other. It is complete in itself. Like Earth, it stands alone, and in that solitude there is a kind of dignity, a kind of beauty that multiple moons might have diminished. When the astronauts of Apollo 8 first saw Earth rise over the lunar horizon, that famous Earthrise photograph, they said it changed them forever. Seeing Earth as a small blue marble, fragile and alone in the vast darkness, with only the moon for company, that image became an icon of the environmental movement, a reminder of how precious and unique our world is. Would that image have been as powerful if there had been 2 moons in the frame, or would it have suggested that Earth was less alone, less vulnerable? The poetry of moons is ultimately the poetry of loneliness and connection, of distance and longing, of cycles and return. The moon is close enough to see, to map, to know intimately. Every crater, every mare, every mountain. Yet it's far enough to remain mysterious, unreachable for most of human history, a destination for our dreams more than our bodies. And here's the deep truth I keep returning to. We don't write poetry about things that are ordinary. We write poetry about things that move us, that mystify us, that make us feel less alone in the universe. The moon does all of these things. It connects us to our ancestors who gazed at the same moon. It connects us to lovers across the world who look up at the same moment and think of each other. It connects us to the cosmos itself, reminding us that we are not separate from the universe but part of it, made of star stuff, accompanied by a celestial companion that was born from our own body. If we had 2 moons, we would have written different poems, told different stories, dreamed different dreams, but would they have been better? Or would the abundance have somehow diminished the mystery? There's something powerful in having exactly 1 moon, not 0, which would leave us truly alone, and not 2 or more, which might divide our attention and our affection. 1 moon, perfect in its imperfection, constant in its changes, bright enough to light our way, but not so bright as to hide the stars. The Japanese have a tradition called tsukimi, moon viewing parties where people gather to appreciate the beauty of the full moon, to write poetry, to eat rice dumplings shaped like the moon. It's a celebration not of the moon's utility, but of its pure aesthetic presence, its gift of beauty to the world. Would we have needed 2 separate festivals for 2 moons, or would we have waited for those rare nights when both were full, throwing celebrations that would have made our current full moon parties seem quiet by comparison? I want to leave you with one last thought, one last piece of poetry made real. The moon, our moon, is moving away from us. Every year it grows a little more distant. In about 600 million years, it will be too far away to create total solar eclipses, that perfect cosmic coincidence where the moon exactly covers the sun will be lost forever. We are living in the only epoch in Earth's history when total solar eclipses are possible. We are the lucky ones, the ones who get to see the diamond ring of the corona, the sudden darkness at midday, the stars appearing in daytime. This is its own kind of poetry, that we exist at exactly the right time to witness this celestial perfect alignment. Too early, and the moon would have been too large, blocking too much. Too late, and it will be too small, unable to fully cover the sun. But right now, in this moment of cosmic time, everything aligns perfectly. That's what the moon teaches us. In the end, that beauty is temporary, that perfection is fleeting, that we should gaze up while we can, write our poems while we have the words, love under the moonlight while it still graces our nights. Whether one moon or two, whether bright or dark, whether waxing or waning, the moon reminds us that we are part of something ancient and ongoing, something that began billions of years ago in violence and chaos, and somehow became beautiful, became meaningful, became poetry. So go outside tonight, if you can. Look up at our moon, our only moon, our perfect moon. See it not just as a rock in space, but as Earth's companion, Earth's child, Earth's eternal dance partner. See in its face all the faces who have ever looked up at it, all the lovers, all the poets, all the dreamers, all the children making wishes, all the sailors navigating home. See yourself reflected in that ancient light, connected across time and space to everyone who has ever lived under the moon's gentle gaze. And perhaps whisper a small, thank you. Thank you for being exactly one. Thank you for being exactly where you are. Thank you for the tides and the light and the dreams and the poetry. Thank you for being the moon. Not a moon, not one of several, but the moon, singular and irreplaceable, eternal and ever-changing, distant and intimate, silent and speaking volumes to anyone who takes the time to listen. This is the poetry of moons, that in their light, we see ourselves more clearly. In their cycles, we understand our own changes. In their beauty, we find inspiration to create beauty of our own. And in their singular presence or imagined multiplicity, we discover that the universe is far stranger, far more wonderful than we ever dared to dream. The moon will be there tomorrow night and the night after, and for billions of nights to come. Each night a new poem, each phase a new verse, each cycle a complete story that begins again the moment it ends. This is the gift of our one, perfect, irreplaceable moon. This is why we write poetry about it, why we always have, why we always will. Until the last human voice falls silent, there will be someone, somewhere, looking up at the moon and finding in its light a reason to hope, to dream, to love, to create. That's the true poetry of moons, not what we project onto them, but what they inspire within us. And that brings us back to our question, not to answer it, but to hold it like moonlight in our palms. What if Earth has had more than one moon? The question itself becomes a kind of poetry, doesn't it? A reminder that even the most permanent seeming features of our world, that bright companion that has watched over every human who ever lived, might have been different, might still become different. Perhaps the moon knows. If rocks could remember, our moon's highlands might whisper of an ancient sibling, of a slow celestial embrace that ended in union rather than farewell. Or perhaps those crater-scarred plains have always been alone, the sole witness to Earth's transformation from molten fury to living world. We search for certainty in orbital mechanics and isotope ratios, but some mysteries prefer to remain mysteries. Picture yourself standing at the edge of an ancient ocean 4 billion years ago. The sky above you holds a moon so close you could almost imagine touching it. Maybe there's another light there too, smaller, faster, racing through its own orbit like a bright thought across the mind of night. You're watching not just moons but time itself, compressed into celestial motion. Each orbit is a heartbeat, each phase a breath. And in their dance you can almost see the future folding and unfolding, the tides that will one day carry life from sea to shore, the stable tilt that will paint seasons across continents not yet born. The poets have always known what the scientists are still discovering, that the moon is more than rock and regolith. It's the keeper of rhythms we feel in our bones, the pull of tides in our blood, inherited from ancestors who were themselves mostly seawater. Whether Earth had one moon or many, we are all children of gravity's slow sculpture, shaped by forces that work in deep time, patient as starlight. Stand outside tonight. Look up at the moon, our moon, Earth's moon, the only moon we've ever known. Let yourself wonder not just about what was or what might have been, but about what it means to live on a world where such questions can be asked. Every crater you see is a story of cosmic chance, every mare a memory of ancient fire. In its light, we are all temporary, and we are all eternal. What if Earth has had more than one moon? The answer drifts somewhere between yes and no, between the precision of orbital dynamics and the soft uncertainty of deep time. Perhaps it's enough to know that we live in a universe where moons can be born and lost, captured and released, merged and shattered, where even the most faithful celestial companion is, in the end, just visiting. The moon will set soon and rise again tomorrow night, as it has for longer than memory, longer than life, longer than the continents themselves. And somewhere in that certainty lies the most beautiful uncertainty of all.